all right, let's do it. Level up. All right, I love level up. It's one of my favorite things. Hey, if you're a teacher, if you're a student, if you're just a person who loves to do math, then come on back. Well, first you should download it, perform the operations, perform all the math. Come on back and see how you did. Don't forget to give me a thumbs up. Don't forget to subscribe and tell everyone all about me. All right, let's do it. Make sure those electronic devices are put away so we can clock it and lock it, my people. All right, let's refer to the given table. There's the given table. All right, we want to calculate the slope. Well, from a table, we find the slope by doing the change in y over the change in x. This is a y. It is a fancy way of saying y. It's called function notation. It's called f of x. But it's still the output. It's still the y. And then there's the x right there. Okay, so notice the y is changing by adding 6. So that is 6. The x is changing by, looks like adding 3. Oh, that's a terrible 3. There you go. Make sure you reduce those slopes. That ends up just being 2. You can write it as 2 over 1 if you want. Let's identify that y-intercept. Hey, do you remember what is true about the x value at the y-intercept? That's right. Look on the table. The x value is 0 at the y-intercept. Make sure you write the y-intercept as an ordered pair. So that's 0, 12. Now we're going to write the equation y equals mx plus b. But notice we don't have a y. We're talking about a special character named f of x. F of x is a function. For every input, there's one and only one output. That's what a function is. So we're going to call it f of x equals the rate of change times your input variable plus your initial value, or the b, which is the y-intercept. All right, let's keep going. Let's calculate the slope. To calculate the slope, you do rise over run. Notice we have lattice points. That is not a lattice point. That is not a lattice point. That isn't. That isn't. That is right there. Okay? So I'm going to go down and over. I always go from left to right. Okay, so when we find the slope of a graph, we look for rise over run. The rise is 1, 2, 3, down 3. The run is 1, 2, 3, 4, over 4. There it is. Identify the y-intercept. Well, the y-intercept is where you cross the y-axis. So the y-intercept is right there. So it looks like 2. And remember, the y-intercept is always an ordered pair. So 0, 2. Let's write our function. Output variable is y. Rate of change is negative 3/4. Input variable x plus b. If b is negative, then I would put minus b. All right, let's keep going. Okay, now it looks like we're going to graph lines in slope-intercept form. All right, we're going to graph lines. So we have this thing called g of x. Remember, g of x is just the name of the function. It's still an output variable. Right? It's still y, it's just we're calling it g of x now. It's got a name. I'm going to make this g of x yellow. All right, so I'm going to identify the slope. The slope is the number in front of x. There is my slope. Change in y over change in x, or rise over run. The y-intercept is that value right there. As an ordered pair, x is always 0 at the y-intercept. Let's graph it. I'm going to go down where y is negative 4. And now I'm going to apply my rise over run. Up 1 over 2, up 1 over 2, up 1 over 2. I like to do a few of them, especially when we're graphing numerous graphs on the same coordinate plane. And make sure you're really kind of accurate with this, right? We want to be accurate. Drive your lines all the way through. Arrows go on the ends. Just like that. All right, that looks good. Remember, that one's yellow. Okay, now the next one, h of x, is going to be orange. There's my slope, negative 2. I like to make it a fraction, so because it's not a fraction, it's an integer. To make it a fraction, just put it over 1. The y-intercept is right there, 0, 6. All right, let's go to 6. 1, 2, 3, 4, 5, 6. Now I'm going to go down 2, and then I'm going to go over 1 in the positive. Down 2, over 1. Now I'm going to see if I can hit this line. I did right there. Okay, so I feel pretty confident that's going to be the point where they intersect. All right, draw that line. Make sure you drive it all the way through. Arrows on the end. Arrows on the end. And then make that orange. All right, that looks happy with my work. I'm really focused today. All right, let's do this one in pink. Okay, slope. There it is. Y-intercept. There it is. As an ordered pair. All right, let's graph it. 0, 1. Right there. Down 3. Over 4. Ooh, we landed in that spot. Down 3. Over 4. All right, let's go ahead and draw that line. Okay. Arrows on the end because it goes on forever. All right, that's going to be pink, so I'm going to make it pink. Oh, that was a little sloppy. But now, do all the lines intersect at one single point? Yes. Yes, they do. What is that point? Well, let's see. It has a y value of 4 and an x value of -2. I love that problem. All right. Let's keep going. Looks like we have a function now. Donovan's cat, Fluffy, had a baby kitten. His favorite kitten weighed 2 ounces at birth and gained an average weight of 3 ounces per week. All right. There's the function for that. Notice this is your rate of change, and I know it because of that word right there. All right? And also, we had an initial weight, right? 2 ounces at birth. That's the initial weight. That's times 0. So what is the initial amount? 2. 2 what? 2 ounces. Identify the rate of change. Well, look, these are right in the problem. 3 ounces per week. OZ is an abbreviation for ounces. Highlight the initial value and rate of change in the word problem above. All right? Well, the initial value is right there. And then the rate of change is right there. Write the given function. Oh, all right, they just want me to repeat it down here. I'd like to do that. Just to identify. We call that function w, and the input value is x. And this is the rule that changes x, the number of weeks, into the weight, the output, right? Number of weeks is input x. When I simplify it, that represents the weight of Fluffy, w of x. All right, the model w of x is valid for only 32 weeks. Ooh, that's important. That is important. Now we have a maximum value. A lot of models have a min and max value. We're going to create a table where weeks is the input x and the weight is the output w of x. All right, my minimum is 0. That's when Fluffy was born, 2 ounces. My maximum is right here. The model is only good for 32 weeks. After that, it's extrapolation. The model is no longer good. Now you're just approximating based on what you've learned. Okay, now you got to pick some ordered pairs in between. So I'm just going to pick 10, 20, and 30. I just want to make it easy. All right, I'm going to put these values in one at a time. So now, I'm going to go 3. Remember, x is number of weeks, so 3 times 10 plus 2. Fluffy was 32 ounces. Now I'm going to put in 20. 3 times 20 plus 2. Man, Fluffy's gaining weight quick. I think they're overfeeding that kitten. 3 times 30 plus 2. Woo! Fat cat. Now the last one is 32 plus 2. And we will never go past that in this model. 98. Fluffy is Fluffy. All right. Now we're going to graph it. Okay, so this is weeks. And I'm going to do increments of 3. And this is weight. And I'm going to do increments of 10. Okay, so that's 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. All right, so every increment represents 3. And I skipped them because it'll get jumbled. You know what I mean? So 3, 6, 9, 12, 15, 18, just counting by 3s. Now I'm going to count by 10s. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. You like to try to get about 10 increments in or more, okay? You could have gone by increments of 2 here. You could have gone by increments of maybe 8 or 7, but I like nice numbers, all right? 2 would have been good, but I like to keep them about even, same number of increments. That's just my choice. All right, 0, 2 is about there. I'm going to approximate that. 32, 96. So here's 33, so it's a little bit less than 33. And 96 is a little bit less than 100. So I'm going to say about there. Now, time is always continuous. So I'm going to connect these two. I don't have to do the other 3 ordered pairs because they're automatically going to show up on this. And I'll show you what I mean by that. If I do the minimum and maximum, right? This is my min. This is my max. And because it's linear, those other ordered pairs will automatically show up. So for example, 10, 32. Bam. Right about there. And that's perfect. 20, 62. 20, 62. Just above 60. Woo, that's perfect. And then 30, 92. Just above 90. Man, that's good stuff. Okay. Notice my graph ends there because anything past 32 weeks is speculation. All right? It doesn't count in the model. It's called extrapolation. When you try to find numbers outside of the min and max value of a model, that's extrapolating. Identify the minimum and maximum input values. Well, the minimum input values is 0. The maximum is 32. Identify the minimum and maximum output values. Well, the minimum is 2. Maximum is 98. How much did the kitten weigh after 19 weeks? Well, to figure that out, I'd have to do 3 times 19 plus 2. I'm going to put that in my calculator. 3 times 19 plus 2. 59 ounces. How many weeks did it take for the kitten to reach a weight of 86? Well, that's my output. So now I'm going to set my output equal to my function rule. Solve that for x. Subtract 2, subtract 2. 84 equals 3x. Divide by 3, divide by 3. 3 goes into 8 twice. 28 equals x. So 28 weeks. Is the graph increasing or decreasing or both? Well, it's going up the entire time. Decreasing is when you go down from left to right. Increasing is when you go up from left to right. So this thing is always increasing. Woo, all right, one more level to go. You're doing great. Keep it up. Uh-oh. Gallons of water in bathtub and minutes draining. All right. So you took a bath, right? You pull the plug. This is how long it takes the water to drain out of the tub. So that's exactly what it's describing. Time it takes for water to drain from tub. Woo, that's all. All right, what was the initial amount of the water in the tub? Well, look, I get a lot of confusion on this one. The graph, right, the actual graph goes up to 50, but the function doesn't. the function stops at 42. So I'm going to assume that is the initial amount of water in the tub. And please put unit of measurement. That would be gallons. What is the average rate of change? All right, well, from there to there, we go down 42. And from there to there, we go over 7. So my rate of change is negative 42 over 7. That's negative 6. Again, unit of measurement. Negative 6 gallons per minute. That's what that means, GPM, gallons per minute. D, what are the minimum and maximum input? Well, 0 is the minimum, 7 is the maximum. And 0 and 7 what? Minutes. Okay. What are the minimum and maximum output values? Well, the minimum is right here. That's 0 gallons. The maximum is right there. That's 42 gallons. According to the model, how many minutes pass before the tub is completely empty? Well, it empties right there. So 7 minutes. Let's write a function. Okay, we're going to call it g of m. So the output variable is g of m. The input variable is m. So it's g with an input of m equals your rate of change. It's decreasing, so it's negative 6 times your input variable plus your initial value. That's done. What is the maximum number of gallons the tub holds? That's a tough one. But I think I'm going to say that it was full right here. So I'm going to say 42. Again, this is just an axis that gives us enough room to graph everything. That doesn't mean the tub holds 50. That just means I can graph up to 50. But the maximum value on the function is 42. So I'm going to say 42 galones. How many gallons of water were left in the tub after 3 minutes? Well, let's see if we can do this here. So here's 3. Boom. There's that. 24 gallons. Now, if I use the model, that would be negative 6 times 3 plus 42. Negative 18 plus 42. Hey, that's 24 as well. So look, the graph gave me 24, and the model gave me 24. Supermodel. How many minutes did it take for the tub to have 12 gallons of water left in it? Well, let's see if this works this way as well. Here's 12 gallons, so boom. And what is that, 5 minutes? All right, well, let's see if it worked. And I'm going to use the model to see if it works. So remember, this is your output. So I'm going to go g of m equals 12, and I'm going to set that equal to the model. Subtract 42 from both sides, get that constant term over there, right? Inverse operations. Now I'm going to divide both sides by negative 6, and I get 5. Hey, that's what we got. Let's go. That was good mathing today. Good mathing. I think we're getting it. That's what hard work does. Well done. Well done. All right, stay strong. Don't forget to subscribe. Tell your friends all over the world. See ya.